Welcome again. The last class we discussed some basic properties of homomorphism, and we try to prove all these properties of a group homomorphism. Now, in this class, we continue the some other properties of this group homomorphism. So, we just start today class with this theorem where we say that phi from G to G1 be a homomorphism. I take this G is simply is the star. I am not writing the star here, and this G1 with the another binary operation. So, this means G1 and G2 are two different binary operation. If we have a so a phi from G to G1 is a be a homomorphism. Then the first is say that if H is a subgroup of a G and H1 is nothing but is equal to phi of H. So, we can say that simply if H is a subgroup of a G, then phi of H is a subgroup of a G1. And so, we simply say that if we have a H is a subgroup of a G, then I denote it as H1 is the same as a subgroup of a some G1, and this is nothing but is equal to you have a phi of H image of this, and this is again is a subgroup of a the another group is a G1. Similarly, if this is normal, then phi of H is normal in G1, and again we have to say that if H1 is a subgroup of a G1, then H is nothing but is equal to, because we have a phi of G to G1, then we have to write H is equal to nothing but is equal to phi inverse H1 is a subgroup of a G, and if H1 is a normal, then phi inverse H1 is a normal in G. So, we have a this is a try to prove this theorems. Because of proving the normality, we have to we combine this, we have to directly, if this is the two parts A and B and D, we can simply say that H is a normal in G and phi is onto that we have to condition imposing this, and then for a subgroup there is no need of imposing this condition. So, this if H is only subgroup, then phi of H is a subgroup, but for a normality H is normal and also phi is onto, then we can say that phi of H is a normal, and similarly for the this is a for a subgroup for a H1 is this. So, let us try from the first one, because we have a phi of G to G1 be a homomorphism. If H is a subgroup of a G, and then if H is a subgroup of a G, means we have a clearly H is a non-empty and A and B are the element of H, then this implies that A B inverse also the element of H. So, then we have to show that phi of H is a subgroup. The phi of H is a subgroup means we have to take a two some elements of phi of A1, phi of A and phi of B are the element of a G1. Then we have to show that phi of A, phi of B, A is the element of a G1. Then we have to say phi of A, phi of B ka inverse is also the element of a G. If we show that, then we can say that phi of H is the clearly is a inverse of is a homomorphism of a is a subgroup of this set. So, let A and B are the element of H1. A and B are the element of H1 means there is a is equal to phi of A and B is equal to phi of B, where A and B are the element of H. So, by this property we can say that in this form. Now, because of this we can say that A1, so with A1 B1 is the element of A1 and we have taken B1 is the element of H1, means we have to show that A1 B1 inverse is also the element of H1, means we have to show that phi of AB inverse is the element of a H1 like this. So, we have to try to prove into this form. Okay, so let's we have to take A and B A1 B1 as the element of H1. Then by the definition H1 A or B are the element, the A1 can be written as a phi of A and B is phi of B. A1 B1 inverse can be phi of A, phi of B inverse. Now we know the property of this phi of B inverse can be written as a phi of B inverse. We can use this equal to phi of B inverse, the same as a phi of b ka whole inverse. So phi of b ka whole inverse can be written in this form, and now phi of ab inverse, and now a and b are the element of H, then a and b inverse is also the element of H, because H is a we have a subgroup of a G. So this means phi AB inverse also the element of a phi of AB inverse is, so this is the element of a, clearly is the element of a H1, because this is the element of a H, and if this is the element of H, this is the element of H1, then we have to show that this is a A1, B1 inverse is the element of a H1, so this one H1 is a subgroup of a G. This completes the proof of this part. First, we can simply say that if we have a take a two elements A and B is the element of A. This one is clearly this is non-empty because of we have to non-emptiness, because H1 is equal to the C E1 E is the element of H, and phi of E is equal to E1. E1 is the element of a you have a this is the this is the element of a H1, and then H1 is equal to E is the element of a G1. This clearly this is not a problem. So if phi of E is the element of a clearly this we have a this H is a phi of H is clearly H1 is clearly is a non-empty. So this is the non-empty, and then the second condition is also solved by the subgroup criteria. So we can say that this H1 is a clearly is a subgroup of a group of G. Now next we try to prove the this H is a normal, but we have to using the one more condition. That condition is saying that if we have a this homomorphism, and H is a subgroup, and also phi is onto. So we have to using the onto-ness here. So we have a already this is a if phi is H is a H is a normal, and then H is a subgroup. So this means we have a this we have to show the phi H is normal. So let phi if H is a normal, then H is a subgroup. H is a subgroup, then the H1 is a subgroup. The first condition is trivially hold. Now we have to show that only that this is a normality condition. So normality condition means we have to take any element of a G is the element of a G, and then we have a some H1 is the element of a H1. Then we can show that G of H1 and G inverse is also the element of H1. If we have to prove that this is also the element of a H1, then we can say that clearly this set is a normal subgroup of this. So G1 is the element of a G1, and H1 is the element of a H1 is equal to phi of H, and then because phi is onto, so there exists some H belongs to the H such that H1 can be written in the form of a phi of H. Because of since onto-ness, if there exists G1 is the element of a G1, then there exists some element G where phi of G is equal to G1. So if phi is clearly onto, that means there exists at least one element G1 is the element of a G1, corresponding this there one element is exists into G, then we can say that phi of G is the same as a we have a G of 1. So this means by the onto-ness we can say that phi of G is equal to G1. Now we have to try to show that GH1 G inverse is the element of H. So we starting from this phi G1 H G1 inverse, because G1 is the element of a this G1, because we have to show that this is inverse normal in G1. So if it is normal in G1, then we can take a G1, G is the element of a some G1, and then this is also the element. So this means we can say that we take any two element G H1 and G inverse. Now G1 is equal to by the onto-ness, this can be written as a phi of G, and H1 can be written as the because of a phi of H1 is the same as the phi of H. So this can be written as a phi of H, then this can the phi of G ka inverse. Now we have to using the property again, phi of G inverse is equal to say the phi of G ka whole inverse. So this is an whole inverse, then phi of G, phi of H, and then phi of G ka inverse, because phi from G to G is a homomorphism. So we can say that this phi from G H G inverse, and now we can H is a normal in G. So if we have any element of a G belongs to G and H is the element of a H, then we can say that G H G inverse also the element of H, because since H is a normal in G. So, if H is a normal in G, so that means this is the element of a clearly is the element of a H, and this is if this is the element of H, this means this whole thing is nothing but is equal to, we can write as a phi of H, and this is equal to H1. H is a normal this condition. By this condition we have to, so this implies that this is the element of a this phi of this is the element of a phi of H. If this is the H1, then we have to show that this is means G1 H1 G1 inverse is the element of a H1, and then if this is the element of H1, then H1 is equal to H1 is nothing but is equal to, you have a same as a phi of H, and this is a normal into G1. So, this means this we complete the proof of this theorem. This result, if H is a normal and phi is onto, then phi H is normal in G1. Okay. So, now next we have to try to the inverse part of this. So, inverse part of this means we have a phi from G to G1 be a homomorphism, and H1 is a subgroup of a G1. So, now here we have a H1 is a subgroup of a G1, and so this H1 is a subgroup of a G1. You have a phi of A, phi of B is the element of a H1, then simply you have to just take a, and then you have to phi of A and phi of B ka whole inverse is also the element of H1. So, we can just simply say into this form. So, let A and B are the element of a H. So, we have to show that AB inverse also belongs to the H. So, AB is the element of H, H is equal to, you have a phi of inverse of H1. So, this is phi of is inverse of H. So, this is phi of inverse H1 can be written for X is the element of a G, phi of X is the element of a H1. So, this means because phi of G to G. So, if we have a X is any element of a G, then this is a map of the phi of X, and that phi of X is the element of a this, because H1 is a subgroup of a G1. So, if we take a this thing as phi of inverse of H1 is the form of a this form. Now, phi of phi inverse H1 is this form. So, if we take a phi of A and phi of B are the element of a two elements of a H1, and because H1 is a subgroup of a G1, then phi of A, phi of B ka whole inverse is the element of a H1. So, by the property of a H1 is the inverse, using the inverse property we can say that this is the element of a clearly phi of A, phi of B is the element of H1, and because H1 is a subgroup of a G1, so phi of A, phi of B ka whole inverse is also belongs to the H1. So, if this is the element of H1, then because we just try to this phi of AB inverse, and now phi of AB inverse can be written in the form of because this phi is a homomorphism. If phi is a homomorphism, phi of A, phi of B inverse, and now phi of B inverse is the same again the property of a phi of B inverse is the same as a phi of B ka whole inverse. So, this can be written phi of a phi B inverse, and now by this H is a H1 is a subgroup of a G1, then this quantity is completely belongs to the H1, and if this quantity is completely belongs to the H1, this means phi of AB inverse belongs to the H1. So, this implies that phi of AB inverse belongs to the H1. If this is belongs to the H1, then we have a phi inverse H1 is equal to this form. Phi of X is the element of H, or X is the element of a G. This means AB inverse is the element of a AB inverse the element of a H, and AB inverse as the element of a H means H is a subgroup of a G. So, this means AB are the element of a H, then H1 can be in the form of this form. So, this means we can say that AB inverse is the element of H. So, hence H is a subgroup of a group G. So, this means clearly we have to prove this the third part of this theorem C part, where phi is a homomorphism and H1 is a subgroup of a G1, then phi inverse H1 is a subgroup of a G, and H is a in the form of a phi inverse H1, and that is a group of is a subgroup of a G. Okay, so now we have to the next part, where we say that phi from G to G1 be a homomorphism, from and H1 is a normal subgroup in G1, then we have to try to prove that this H is equal to H inverse is a normal in G. So, we take any element G is the element of a G, and H is equal to written in the form of as the H is equal to as the H is phi inverse H. And now, if G is the element of a G, then phi of G is the element of a G1, and phi of H is the element of a H is the element of H, then phi of H is the element of a clearly is a H1. And since H1 is a normal in G, so we have to, if H1 is a normal in G1, so you have a this is equal to phi of G, phi of H, and phi of G ka whole inverse is the element of we have to just say that this is the element of a, we have to show that if this is the element of a H1, and if this is the element of H1, this can be written in the form of a this means if this means this we have to write into this form. So, phi is the element of a, clearly this is a normality. So, this is the element of a H1. So, this is the element of a H1. If this is the element of a G inverse is the element of H1, then G inverse is the element of a phi of inverse H1, and phi of inverse H1 is equal to H, and then for any G H, therefore H is a normal in G. So, we can start from this because we know that this is the element of a H1 because H1 is a normal. If this is normal, then we can use the property of this inverse property, then we take a homomorphism, then we have to phi of G H G inverse, and this is the element of a H1. This means this is the whole is the element of a H1, and this whole is the element of a H1 means phi of G H G inverse is the element of a H1. So, this means if this is the element of H, then we can say phi inverse this is the element of a H1 inverse, and this is the H1 inverse psi inverse H1, and the inverse as phi inverse H1 is equal to you have H for any G, and this therefore we can show that this H is written in the form of phi inverse H1 is normal in G. So, now we just complete this all the 4 parts of this result, where we have to show that if we have a phi from G to G1 be homomorphism, if H is a subgroup, then H is equal to H1 is equal to phi of H is a subgroup in G1, and another we have a, if we have a H1 is a H is a normal in G and phi is onto, then we have to show that H1 is equal to phi of H is a normal in G, and next we have to show that if this homomorphism and H1 is a subgroup in G1, then H1 is equal to phi inverse H, phi inverse phi H is equal to phi inverse H1 is a subgroup, and then we have to show that is also is a normal into a G. So, this complete the proof of this result we have. Now, we have to move to the next we have observed that every homomorphism determine a normal subgroup by its kernel. Although it may not initially be clear that a factor group corresponding exactly to harmonic images, homomorphic images, we can use a factor group to analyze the homomorphism. Okay, for any group homomorphism from G to G1, there is associated is a normal subgroup of a G, namely kernel of a phi. We already show that the kernel of a of this homomorphism is clearly is a normal subgroup. Conversely, the following theorem demonstrate that every normal subgroup of a group give rise to homomorphism, and that known as a natural or canonical homomorphism. So, let us this is the theorem. We can say that this is called as a natural or canonical. We show that kernel of a phi is a homomorphism. Let G be a group and N be a normal subgroup of a G. Then the map phi from G to the quotient group G by N defined by phi of x is equal to is a coset of Nx is a homomorphism from G on to G factor group of a Gn. The kernel of phi is precisely the set of because we just know that the kernel of a phi is equal to map the identity, and now you know that the identity element of a G by N is equal to, we have a N is the identity element in this G by N. So, we know that the identity element of this factor group is N. So, we try to show that this we have a condition is this N is a, because of the factor group we define, N should be a normal subgroup. So, we take a G is a group, N is a normal subgroup, then this G by N is a sense. So, there is a map we have defined phi from G to G by N defined in the form of a phi of x is equal to Nx and is a homomorphism. Now, the first question is very thing, if you have whatever map we have to define, this should be a well defined first, and then we have to only say that this satisfy the homomorphism condition, preserve this mapping to this. Okay. So, the fact the mapping is phi is homomorphism direct from the manner which is multiplication is defined on the quotient group. So, now adjust it. For any xy is equal to this, phi of xy can be written as a nx ny, and then you know that the nx ny is equal to phi of x, phi of y, and then the phi of xy can be written as a this thing. So, means is clearly we can trivially can say that this is a homomorphism. Moreover, phi is onto because if we have nz belong to the z, there exists n belongs to the z such a phi of z is equal to nz, and this implies that this G by N is a homomorphic image of G, because we have to show that this is clearly is a this is a homomorphism of G onto G, the kernel of phi precisely this, and then we have to say simply this, if moreover if we have a phi is taking is a onto, if phi is onto, then phi of z is equal to this, means G by N is a homomorphic image of a this G. So, if we have a homomorphism and onto-ness, then we can say that G by N is a homomorphic image of this group of a G. Since the cosets N is served as the identity element of a this, so kernel of a phi is equal to this, and now you Nx is equal to this, so you have to just completely N is equal to there. So, we just say that kernel of a phi is nothing but is equal to is complete the this normal subgroup, we have to just say that. So, okay, this is the proof. We have to now try to we try to prove the one more result. So, that result is saying that if phi is a G to G1 is be homomorphism, then phi is a 1 1 if and only if kernel of a phi is equal to identity. This is very interesting and trivial result when we say that for proving that 1 1 then we can simply say that kernel of a phi is equal to identity. If a kernel of a phi is equal to identity, then we have to say that is a 1 1, and if it is 1 1, then we have to show that is clearly is a condition hold. And now we have to just a kernel of a phi is equal to identity, means you have to take a any element of a x in the kernel of a phi, and then you show that x if is the element of a kernel of a phi, then if x is the element of a kernel of a phi, then kernel of a phi of x is equal to, you have a identity of a E1, and then identity of a E phi of x is equal to identity of E1, and then you have to show that you take any two elements of a this, then phi of x1 is equal to phi of x2, then y phi is if kernel of phi is equal to identity, then you have to show that is a 1 1, and then second one is a, if it is 1 1, then you have to show that the kernel of a phi is an identity element. So, since suppose phi is a 1 1 function, then E is the element of a kernel of a phi. So, I am to show that the only element in this kernel. We know that the kernel E is the element of a, this is a kernel of a phi. Now we have to show that this is the only element which is in kernel. There is no other element in this identity is equal to this. So suppose if there exists another element A belong to the kernel phi A is not equal to E. So then we would have a phi of A is equal to E1 and phi of E is also E1. So because we have E is the kernel of a phi, if kernel of a phi means f of E is equal to, you have a E1 identity, and we have to take some another element, A is the element of kernel of a phi, and then this is A is not equal to the identity element, that means phi of A is also is equal to identity, is the E1, and now we have a phi of E is equal to E1 and then is equal to phi of A, and then but you know that this implies that you have a phi of E is equal to phi of A, and phi we have to assuming that is a 1 1, and then this implies that A is equal to identity, which is a contradiction because A is a, we have to taking A is not equal to identity. So this means if A is equal to A into A, phi of A is equal to phi of E, but we have a given is identity, but A is not equal to identity. This means this is contradicting the fact of our hypothesis. Hypothesis is saying that we have to phi should be a 1 1. So this, if A, we are assuming that A is not equal to the identity element, that means clearly if phi of A is equal to phi of E is and but A is not equal to E. So this means this is contradicting our hypothesis phi is 1 1. That means our assumption A is not equal to identity is wrong. If we have to take any other element of the kernel that is the same as a identity element. So this means kernel of a phi as only element with the identity. Now we have to try to conversely, suppose kernel of a phi is equal to identity, then we have to try to show that take a 2 element phi of A is equal to phi of B, then we try to show that A is equal to B. If phi of A is equal to phi of B, then we have to we have to show into this form. So we can say that we can because phi from G to G1 is a homomorphism. If we have A and B are the element of a G, then phi of A and phi of B is the element of a G, and then phi of B ka inverse is also the element of a G. So we can say that phi of A, phi of B ka whole inverse is equal to phi of B, and then phi of B ka whole inverse, and then this can be written as a phi of A and phi of B inverse, and then this can be written as a, you have a this is nothing but is equal to, you have a identity E1, and this can be written as a phi of A, and then you have a some B inverse is equal to, you have a is equal to identity of 1, and then you can just say that because of this you can say that A B inverse is equal to E1, that is equal to kernel of a phi, and then kernel of a phi means this is nothing but is equal to, you have a identity. So we can say that clearly AB inverse is equal to identity. If AB inverse is equal to identity means we have a AB inverse B is equal to E of B, and then we have to show that A identity is equal to B, so A is equal to B. So this means we have to prove that if kernel of a phi is equal to identity, then clearly phi is 1 1, and similarly if phi is 1 1, then kernel of a phi is equal to identity. So this we have to just try into this form, just I already explained you in this form. Then we have to say that and the kernel of phi, therefore phi of inverse is equal to AB, and then phi is phi of A is equal to we have a clearly show that into a this form into satisfy this condition. So this is a very important result. Whenever we have to try to show that the function is 1 1, we try to find the kernel, and if the kernel is equal to identity element, then we can show that this clearly this set is a 1 1. So you just any map, if we have to try this, you have remember this, you have a Z to 2Z, and then we know that the kernel of this phi is equal to, you have a identity 0, and then clearly you can say that this is by this we can say that this phi is a clearly 1 1. So this means we have the kernel of a phi is equal to, you take is identity, then if kernel of phi is equal to identity, then you have to say that this set is equal to identity. So, try to by this showing that the 1 we have to use the kernel, and if the kernel of that set is equal to identity. So, we have to show that this homomorphism from 1 g to g dash is a clearly is a both ways true. So, we have to simply say that this is equal to if this satisfy, then we have to show that this is all these things. So, now just we discuss there is a more properties. The previous class we using the some basic properties of a homomorphism, where identity preserve, inverse preserve, and we have shown that the homomorphism are subgroup and normal subgroup, and then orders of this. This today's lecture we have to discussing some other properties of a group homomorphisms. So, in the next class we have to also continue some two more theorems for related to the homomorphism, and then we proceed to the isomorphism, where we will discuss some isomorphism, and then we have to move to the important theorem of isomorphism, 3 isomorphism theorems. So, thank you very much for this today class.